This is Lab 7, Counters, Group 19. My name is Emily Ng. The purpose of this lab was to become familiar with an important flip-flop application, be able to implement synchronous counters, use digital simulation software to design and simulate a sequential logic circuit, and to learn about and use asynchronous control inputs on flip-flops. So the first circuit we were to design was an up counter. So this is showing the expected next state values. So a 0, binary 0 goes to a 1 to a 2, 2 to a 3, 3 to a 4, 4 to a 5, 5 to a 6, 6 to a 7, and 7 to a 0, which will loop back around and start over again. So this is the K-map for the most significant bit of our expected next state. So you will see that this is looped twice because we are using hazard-free design. So this means that if there is any one that can be looped with another one that has already been looped, it will be looped. So we get the equation A and B naught, or A and C naught, or B and C and A naught. The next bit is, as shown, we get two loops for a reduced Boolean equation of B and C naught, or C and B naught. So the least significant bit has a top and a bottom row, and these can be looped around to make one larger square, which gives us the reduced Boolean equation of C naught. Now this is how we implement this in LogiSim. So we were supposed to use exclusively NAND gates here, no or and or nots. So I had initially had a NAND gate here, here, and here because I had done my bubble matching incorrectly. But if we want to simulate the effect of an AND and an OR gate, we can use two NAND gates. So that's what I did here. And when you have that in LogiSim, you get a 1, 2, 3, 4, 5, 6, 7, back to 0. And you'll notice that there are no A, B, or C inputs, and that is because the output of this flip-flop is A, this one is B, and this one is C, and those act as the A, B, and C that we saw in our diagrams. The next circuit is a ring counter. This has a sequence of 0 to 1, a 1 to a 2, a 2 to a 4, and a 4 to a 0. And it also includes a reset, which will set this state to a 1. Now we are using don't cares for anything that is not a 1, 2, or a 4 because we will not be having any output in those states. So the next value that we will get from a binary 1 is a binary 2, and then the 2 will go to a 4, and the 4 will go back down to a 1. The K-map here has x's, which can be treated as zeros or ones to suit our needs. We treated these ones as a 1 to make the biggest possible loop, and that gave us the equation of B. This one did the same thing, gave us a C, and then the least significant bit, we did the same thing, but in a column, and that gave us A. This is what this one looked like when implemented in LogiSim. And when we go through that simulation, if we have all zeros, we want to reset to a 1, and then that goes to a 2, a 4, back to 1, 2, and 4. Next was the gray code counter. So this is a little different in that we have the increment input. So anytime that is a 0, we keep the current state. Now when that goes to a 1, the counting sequence is going to be 0 to 1, 1 to 3, 3 to 2, 2 to 0. As seen here, we have a 0 to 1, 1 to 3, 2 to 0, and a 3 to 2. Now this one was also using hazard-free design, so you see that these two can be looped together with two different pairs, and they are giving us the equation A and C, or B and C, or A naught and B. Next have the same sort of setup, which is A and B naught, or A naught and C, or B naught and C. This is how this looks when it's implemented in Logisim. So simulating that, whenever increment is off, the clock does not change it. Increment on, we can go from a 0 to a 1 to a 3, 2, back to a 0. So I had a few errors that I've mentioned before, such as no inputs were very confusing to me, so it took a while to figure out how to use flip-flops as inputs. But also, that I didn't mention was with the reset on the ring counter, having that just be one line to the set of this flip-flop and to the clear of the next two, being able to set that to a 1, that was tricky for me. Applications for what I've learned, I learned that, well, I learned how to build circuits that are better synchronized with the different parts, that have fewer inputs, and this will mean that there can be fewer errors in the circuit. Devices that use counters, a couple I could think of were timers and alarms, odometers, and things such as getting locked out of your Netflix because you put your password in too many times. So I hope you found this helpful. Thank you for watching.